Okay, the key to understanding the fundamental theorem of calculus is first to understand the accumulation function. So here we have a function f defined here. It's a piecewise defined function. And we're going to define a new function g of x. And it's going to be a function of the right bound on your integral. So we go from, we'll say 0 here, up to x of f of t dt. So this is accumulating area in this particular graph for different values of x. So notice that our endpoint, this g is a function of this right bound. So we could see some quick examples. If I did g of 2, that's saying find the value of this integral of f of t dt from 0 up to 2. So the endpoint here is determined by the argument inside of g. And that would be all the area up to x being equal to 2, which here we see is 8, based on my picture. If I did g of 4, that's the integral from 0 up to 4 of f of t dt. So it's going to pick up a little bit more. It's going to go all the way to 4 here, and all of this. So all of that is g of 4. So this is our accumulation. So this is what, 16. And so forth. Then we could keep going. If we did, let's say, g of 8, let's do one more. G of 8 is the integral from 0 up to 8 of f of t dt. So notice we pick up some all the way from, we had the 16, oops, let's change colors, and we pick up this piece right here. So on the top here from 6, we picked up another 2, 8, so that's 4. So this should be 20 on the top. And then we take away some down here, because when we have our function underneath the x-axis, it gives us a negative area. So that's 2 times 3, 6, so that should be a negative 3, so we should have 17 for our accumulation. We'll just do it in green this way, because we take away this amount. Yeah. All right, so that is our accumulation function g. All right, now let's see how this connects us to or gets us to our fundamental theorem of calculus. So let's look at a new function f here, and we're going to define g. So we'll just say that is some a value here, and we'll put x right there. So again, if I define g of x to be equal to the integral from a up to x of this function f of t dt, that's my accumulation. So in this picture right here, it would give us that area right there. But let's consider now g of x plus a little bit more. So x plus h. All right. So I'm going to put that, we'll say that's x plus h. So g of x plus h in a different color would be all, oops, let's make it a significantly different color. All of that area, that would be g of x plus h, which is the integral from a up to x plus h f of t dt. And if I wanted the stuff in between here, that's going to be the difference of those two. So g of x plus h minus g of x is going to be this little red sliver right here, the area between x and x plus h. All right. Now, notice what it's also approximately equal to. Back to our Calc 1 stuff. This is like a rectangle. If I made this rectangle right here, whose area is the height, which is f of x. So this is approximately equal to the area of that rectangle, which is the height f of x times the width, which is the difference of x plus h and x, or just h. So the volume under, the area under the pink curve, our f, from x to x plus h is approximately equal to the area of that rectangle. And in fact, if we divide both sides by h, we could say that as f of x is approximately equal to that quotient, g of x plus h minus g of x divided by h. And in fact, it gets better and better the closer I push x plus h to x. And so I smell a limit coming. So we come over here, let's write it one more time. So we've decided that g of x plus h minus g of x all over h is approximately equal to f of x and will be equal to f of x if we take the limit as h goes to 0 of this quotient, g of x plus h minus g of x over h. And if we can stretch our minds back to Calc 1, hopefully we recognize that this is the definition of the derivative of g. So g prime of x is equal to f of x. Now, to just have it all in one place, remember what we just showed here, that if g of x is equal to the integral of a up to x f of t dt, so g is the integral of f, then the derivative of g is equal to f evaluated at that right endpoint. What? So the derivative of the integral is our function. So if I had g of x is equal to, let's say, 3 up to x of sine of t dt, so notice here, f of t is equal to sine of t, and g is the actual integral, then the derivative of g evaluated at x is sine evaluated at x. One more thing to consider. If we have g of x is equal to, we'll say, a up to some function of x, f of t dt, that when we take the derivative of g with respect to x, it is going to be f evaluated at that right endpoint, but we have a chain rule in place. So we have to come back and take the derivative of that right endpoint. So let's look at a quick example of that. If I had g of x is equal to 3 up to, we'll say, x squared sine of t dt, then g prime of x is going to be this function evaluated here, so sine of x squared times the derivative of that x squared. And that is FTC Part 1.